Hey, welcome. Today, we are pulling back the curtain on the world of computer programming. We're going to break down the basic ideas that power literally every app, website, and piece of software you use every single day. So let's just dive right in.
Have you ever really stopped to think about it? How does your phone's calculator just know the answer to a tough math problem? Or how does Netflix know exactly which show to play when you hit that button? Well, the secret behind all of it is a detailed set of instructions we call a program.
So here's the game plan. First, we'll cover the basics of how we even talk to a computer. Then we'll get into the vocabulary and grammar of code. After that, we'll see how it all works in the real world, and we'll wrap things up with a little challenge just for you.
Okay, so you have to understand, at its core, a computer is an incredibly powerful but also an incredibly literal machine. It can't guess what you mean. It needs super specific, step-by-step instructions for everything. And that's where programming languages come in. They're the translators, the bridge between our creative human ideas and the computer's cold, hard logic.
A really good way to think about this is like writing a recipe for a cake. You can't just tell the oven to bake a cake. No, you have to write out every single step. Preheat the oven to 350 degrees. Mix 2 cups of flour with 1 cup of sugar. Crack 2 eggs. Every single detail in the exact right order. If you miss a step or do them out of sequence, you're not getting a cake. A computer program is just like that. A perfect, flawless recipe.
And just like any spoken language, programming has its own vocabulary. These are the basic building blocks, the nouns and verbs we use to write our instructions. And don't worry, these aren't super complicated ideas. They're actually pretty simple concepts that just let us store and manage information.
To make this all feel a bit more real, let's walk through a simple little program. We're going to teach a computer how to calculate something called a factorial. Now, hey, don't worry if you've completely forgotten your high school math. A factorial is really simple. It's just a number multiplied by every whole number smaller than it, all the way down to 1. So the factorial of 4 is just 4 times 3 times 2 times 1, which is 24. See? Easy.
Okay, so here's our recipe for the computer. First, we give it a number to start with. Let's call it n. Then it creates a little spot for our answer. We'll call that fact, and it sets it to 1. And here's where the magic happens. It starts a repeating loop. It multiplies fact by n, then it subtracts 1 from n. And it just keeps doing that over and over and over until n finally hits 0. And then, bam, it shows us the final answer it was storing in fact.
So those placeholders we used, n and fact, they're a really core concept in programming called variables. Just think of them as little labeled boxes where the computer can store information. And there's a reason they're called variables. It's because the value inside the box can, and usually does, vary or change while the program is running. In our recipe, n was constantly counting down, and fact was constantly growing.
Now, on the flip side of that, you have constants. And a constant is pretty much what it sounds like, a value that is fixed and never ever changes. So when we started our little recipe by saying fact equals 1, that number 1 is a constant. It's our solid, unchanging starting point. All right, so we've got our vocabulary, our variables and constants. But words alone aren't enough, right? We need grammar. We need a set of rules that lets us arrange these words into meaningful sentences, instructions that can actually control what the program does, and even let it make decisions.
These rules, this grammar, are called control structures. And honestly, this is where the program gets its brain. Control structures are what allow a program to analyze a situation and react differently, instead of just following the same single path of instructions every single time.
The most basic, fundamental control structure of all is the if-then-else statement. It all boils down to asking a simple question that can only be answered with true or false. And it works exactly like it sounds. If it's raining outside, then I'll take my umbrella. Else, I'll leave it at home. It's basically a fork in the road for our program, letting it choose which path to take.
And we can use this exact logic in our factorial program. See, factorials only really work for positive numbers. So the very first thing our program should do is ask a question. Is the number n less than 0? If the answer is true, then it just prints an error message. Else, if the answer is false, it knows it's safe to go ahead and do the calculation.
The other big piece of grammar you need to know is the loop. This is how we handle repetitive tasks without writing the same line of code 100 times. And there are 2 main flavors. You've got a for loop, which is like saying, do this thing exactly 10 times. You use it when you already know how many times you need to repeat. But then you've got a while loop, which is more like saying, keep doing this thing while this condition is still true. Our factorial program used a while loop. Keep multiplying and subtracting until n is no longer greater than 0. So here's the big takeaway. These basic ideas, variables, logic, loops, they are the foundation of every single programming language out there. So now let's take a look at how they pop up in some of the actual languages that are powering our world right now.
Let's kick things off with Java. It's used on literally billions of devices, from your Android phone to massive corporate servers, and its whole philosophy is summed up in this one phrase: write once, run anywhere. Now, this was a total game changer when it came out. Before Java, you basically had to rewrite your entire program for Windows, then again for Mac, then again for Linux. It was a nightmare. Java said, nope, write it once and it'll work everywhere.
So how on earth does it do that? Well, it's a really clever two-step process. First, your Java code isn't turned directly into instructions for a specific machine. Instead, it gets compiled into this universal middleman language called bytecode. Then, each device, whether it's Windows, Mac, or whatever, has its own special translator program called the Java Virtual Machine, or JVM. And that JVM's only job is to read the universal bytecode and translate it into the specific instructions for that device. It's brilliant.
Okay, let's shift gears to the web. You hear these three acronyms all the time, and they get confused a lot, but they do very different things. Think of it this way. HTML is all about how things look. It tells your web browser how to display stuff. This is a headline, this is a paragraph. It's the paint, the wallpaper, the layout of a house. XML, on the other hand, doesn't care about looks. It cares about the data itself. It's designed to transport information by describing what it is. It's the blueprint and the materials list for the house. And XHTML? Well, that's basically just a stricter, cleaner version of HTML that follows the grammatical rules of XML, kind of like a prefabricated HomeKit with perfect instructions.
Now here's something that might actually surprise you. If you have ever used a spreadsheet program like Microsoft Excel, say to add up a column of numbers or find an average, you were actually programming. That's right. When you type in a formula like equals sum A1 to A10, you are writing an instruction and giving it to the computer to solve a problem. It uses all the same logical principles we've been talking about.
And that brings us right to our final section. We've gone from these big, abstract ideas all the way to real-world examples. So now it's time to boil it all down. What is the single most important takeaway from all of this? Look, it really comes down to these three things. First, programming is just about breaking down a big, complex problem into tiny, logical, manageable steps. Second, even though there are hundreds of different languages, they're all built on the exact same foundation: variables, logic, and loops. And finally, and this might be the most important one, learning to think this way, in this structured, step-by-step manner, is a superpower for solving any kind of problem, whether it involves a computer or not. And that's our look at the fundamentals of programming. As you can see, it's not some kind of dark magic. It's just a logical, creative way to solve problems. So I'll leave you with a question to chew on. Now that you know what the basic building blocks are, what problem, what tedious task, or what cool idea would you solve by writing a recipe for a computer?